Hi everyone, welcome to the third and final lecture bite of week 3. This lecture bite is on the Great Debate, which was a discussion in the early 20th century which boiled down to what is our place in the universe. So to start off, I'm going to give a little bit of background. If you go out to a dark site away from the city lights and you wait for your eyes to be very accustomed to the dark and you look up, you might see something that looks like this. So you'll see lots and lots of stars in the sky, but you'll also see this band of milky colors and dark areas that kind of stretch all across the sky. This is called the Milky Way, and this has been one of the things that's fascinated and puzzled astronomers for a very long period of time. So what is causing that milky appearance? What is going on there? So when we got telescopes, we were able to answer this question. So it's a pretty simple matter of looking at a patch of sky outside of this band, outside of the Milky Way with a telescope, and comparing it to what it looks like when you look at the Milky Way with a telescope. So outside the Milky Way, if you point your telescope at just a random patch of sky, it looks something like this. You'll see occasionally some stars, not too much else going on. But if you look at a region of the sky in the Milky Way, in this band, all of a sudden, there are tons and tons and tons of stars. So really, this is not a Milky Way at all. This is just bunches and bunches of stars that appear to blend together to our eyes because there are just so many of them and they're so close together that we can't tell, and we think it just looks like a continuous milky pattern. But really, it's tons and tons and tons of stars just all shining together. So if we observe the entire sky, that was only part of the sky that we saw in that first photo, and we look at where the Milky Way falls, it turns out that it stretches its entire circumference all the way around the sky, and it cuts our sky in half. There's about as much sky to the north of the Milky Way as there is to the south of the Milky Way, all around if you average out the entire sky. This is what it looks like. So what does this tell us about what the Milky Way is and what the structure of this group of stars that we're in is? So to think about this, I want you to imagine the analogy that you're in a crowd of a bunch of people. And if you look around yourself in 360 and in all dimensions, all the way around, left, right, but also up and down, what you can notice is that you see when you look forward in any direction, all the way around you, you see lots and lots of people along that direction. But if you look up, you don't see many people at all. In fact, you probably will see 0 people standing above you. And if you look down, you won't see any people at all as well. You'll see the ground, and there aren't any people down there. So what you can infer from this observation is that you are in a large, flat distribution of people. There are people all the way around you, but this group of people is much shorter in stature, much thinner in height than it is in width. So you can go hundreds of feet to any side of you and see people, but if you go hundreds of feet up in the air, you will see 0 people there. We can do the same thing with stars. And if you apply this to the Milky Way and the stars in the sky, you can come up with a map that kind of looks like this. So this map was made by William Herschel in 1785. And what he found is that if he looked towards the Milky Way, there were lots and lots of stars. But if you looked out of the Milky Way, out of the plane of this band, this circle that goes all the way around us, there were relatively few stars. And this is a cross section. So in the vertical direction is out of the Milky Way, and the left and right is towards the Milky Way. And the sun is right in the middle of this diagram. So what William Herschel concluded is that we are in the middle of a relatively large, flat, disc-like thing. So how does this work? How far does it extend? Are there stars even further away than we can see with our telescopes that are still in this disk? And are we really in the middle of it? This has been an important question for 100 years after Herschel's discovery. Another question that people thought about around that time is when you look at patches of sky outside of the Milky Way with telescopes, sometimes, most of the time, you'll see something like this where you have stars scattered about. But other parts of the time, you'll see weird structures that look like this. This is what was called in the day a spiral nebula. It's this milky thing, which kind of has this flat, diffuse, nebulous appearance that has this characteristic spiral pattern. So what are these things? Are these galaxies like our own, like the Milky Way in which we live? Or are they some other distant object that's not as big as a galaxy and it's not made up of stars, but it's actually made up of just gas and something else that might be diffuse and might cause it to look this way? And how far away are these objects? So this is what came to be known as the Great Debate. So in 1920, two astronomers debated at the National Academy of Science. And the bulletin for this program, the press release said, this evening, two California astronomers will discuss the size of the universe and present their views as to whether or not there's only one or several universes. And when they say one or several universes, what they really mean is one or several galaxies. Because if there's only one galaxy, then it is the universe. That is the one thing in which we all live. So the two participants in this debate were Harlow Shapley and Heber Curtis. Harlow Shapley's position is that the spiral nebulae are not galaxies like our own. Curtis's position is the opposite. Spiral nebulae are galaxies that are about the same size as the Milky Way and are made up of stars like the sun. And I'll walk through exactly why these two people held these points and what their reasoning was. So first, I'll start with Curtis's argument. Curtis was a believer in these maps of the Milky Way that were made by people like Herschel and later by Kapteyn. And what they did is they looked at the stars in all directions of the sky and they counted them in each direction, and they tried to figure out based on that just how far the stars extended and in which directions were they more prevalent. So what these measurements eventually concluded is that the Milky Way is relatively small. Now, when I say small, I mean astronomical terms. The Milky Way is relatively small at about 30,000 light years across, and that the sun is orbiting, and the sun is positioned near the center of this group of stars. So this figure on the bottom is a map made by Kapteyn. Instead of showing dots to show the stars, he's showing contours of the density of stars. And what he's finding is that most of the stars happen to fall within about 15,000 light years of Earth. So because the Milky Way is relatively small, now let's compare that to these spiral nebulae. Is it possible that these spiral nebulae are about the same size as the Milky Way? So the way Curtis did this was to use observations of what he called new stars or nova. So occasionally, if you observe parts of the sky, you'll see flashes. And even though Curtis and Shapley didn't necessarily understand what was causing all of these flashes at the time, Curtis was able to look at a bunch of flashes in one of the nearby spiral nebulae called Andromeda and measure their brightness. He then compared the brightnesses that he measured of the nebulae or of the nova in Andromeda to nova that he had measured nearby in our own Milky Way. And he found that if the nova are really the same brightness in both the Milky Way and in Andromeda, then that makes Andromeda roughly the right distance away for it to be similar in size to the Milky Way. Therefore, the spiral nebulae are groups of stars that are similar in size to the Milky Way, and they're their own galaxies. They are as much of a galaxy as themselves as the Milky Way is one for us. So that was Curtis's argument. Shapley, on the other hand, took a different tack. The first thing he did was he said, I don't believe these maps made by people like Herschel and Kapteyn. In particular, I don't think that they accurately describe the galaxy, the Milky Way that we live in. And his reason for this is that if you look at stars, you indeed find what Herschel and Kapteyn did. But if you look at objects called globular clusters, which are very tight groups of stars, you see a very different story. So here he's showing a map of the globular clusters that he had discovered and he had mapped in his previous research. So in the top left corner, there's a crosshair. That's the position of the Earth in the sun. And these black dots are the locations of the globular clusters. We're looking right now on a top-down view. And what Shapley found is that these globular clusters are not evenly distributed. They're only found in one direction preferentially, and that is a direction pointing towards the constellation of Sagittarius. So what does this mean? Shapley argues that this means that the Earth is not at the center of the galaxy. The center of the galaxy must be pointing towards Sagittarius because that's where the distribution of globular clusters is centered, and that there must have been something wrong with the star counts done by Kapteyn and by Herschel, because a similar experiment using these globular clusters comes to a very different conclusion. So what Shapley argues is that, in fact, the Milky Way is much bigger than Curtis believes. It's about 10 times bigger. And these globular clusters are what show us that this is actually true. So if the Milky Way must be bigger, then let's look at these nova again, these new stars that are appearing in the Andromeda Nebula. Shapley says, if the Milky Way is actually bigger than we thought, then Andromeda must be further away from us if it is actually the same size as the Milky Way. And if it's further away from us, then these nova must be even brighter than they appear to be in order to potentially look as bright as they do when they reach Earth. And if you do the calculations, Shapley found that these nova must be extremely bright, and what he thought impossibly bright. There's no way that any star could produce as much light as these stars do if that's what they really are. In fact, in some cases, Shapley found that these nova outshone the entire rest of the spiral nebula. So Shapley said, clearly this is impossible. One star can't outshine the other billion in the galaxy. Therefore, this must not be a galaxy. This must be something else, and we must be seeing it in a different way, and it must be closer to us than Curtis was arguing. And finally, Shapley had one other argument that he made, which is that another astronomer named Van Manen had observed one of these nebula, in particular this one, the pinwheel, and found that the spirals were rotating. Now, in our distances lecture, in our speed lecture, we discussed how if you measure a change in angle on the sky, a change in position in right ascension and declination, you have to know how far away that object is to see how fast it's actually moving in physical distance. And what Shapley calculated is that if Van Manen's measurement is correct, and if the spiral nebula were as far away as Curtis thought, then the outer regions of the spiral must be traveling at faster than the speed of light. Einstein told us this is impossible, so these can't possibly be actually galaxies. They must be closer in, which is why their speeds would be relatively reasonable if they're actually moving that quickly. On the other hand, Curtis didn't believe the observations. He thought that they must have been a mistake by Van Manen. So Shapley concluded, therefore, the spiral nebula cannot possibly be as large as the Milky Way, so they are not galaxies like their own Milky Way. They must be something else. And for that matter, they're probably not made up of stars like the Milky Way is either. So who was right? There are a couple of interesting points, and honestly, the debate was kind of a toss-up in the end, after all of the science was eventually worked out in the next couple of decades. In terms of the size of the Milky Way, the maps made by Herschel and Kapteyn were actually wrong. Traditional measurements of the size and the shape of the galaxy were affected by dust, which prevented the star maps from being accurate. So here's what happened. If you look at this map of the galaxy taken with modern data, you can see these dark clouds. Those are dust. This dust is obscuring the light and making it hard for us to see what's going on. And in particular, it makes it hard to see stars because they are fainter after they've gone through the dust. The dust has scattered some of the light away. However, if you look at the same image, the same part of the sky, except using a wavelength of light that's not affected by dust, so using infrared light, this is an image from the WISE satellite, which observes in the infrared, then you can see that pretty clearly there are more stars towards the center of the galaxy than there are towards the outskirts. Here, the center of the galaxy is the middle of this picture here. And this is precisely what Shapley had figured out looking at the globular clusters. There were more globular clusters pointed towards that side of the galaxy than there were towards the edges of this photo, which are pointing the opposite direction. So Shapley was actually right about it. Shapley was the one who figured out that the Milky Way is bigger than was traditionally believed, and that the sun is not at the center of it. The sun is kind of on the outskirts. Now, when everything was said and done, Shapley was not completely right. He thought the Milky Way was about 3 times larger than it actually is. But he had the right idea, and he figured out what the hole in the logic was. So the next thing that we can think about is who was right about the brightness of these nova, or these new stars. So based on the distance to the galaxy, it turns out that Shapley was right, that these new stars were very, very bright, and what he believed to be impossibly bright. But he was wrong in that they're not actually impossibly bright. It was just a new phenomenon that he didn't understand. Eventually, we've come to learn that some of these nova were most likely what we call supernova, which means they're even brighter than typical new stars. And later on in the course, we'll go into what these nova and supernova actually are and what's causing these brightenings of light that Curtis and Shapley were debating about. It turns out that the observations by Van Manen were wrong. There actually is no measurable rotation of the spiral nebulae. Curtis was right to be skeptical of those measurements. So that took away one of Shapley's major points about why the spiral nebulae could not be other galaxies. When you take away that measurement, it turns out that everything is a little bit more plausible. So point Curtis on this one. And finally, who was right about whether the spiral nebulae are galaxies like the Milky Way or not? And the answer came pretty quickly after the debate. So using observations from a telescope in California, Edwin Hubble took images of the Andromeda Nebula. And what he found in the outskirts of this nebula was one star here that seemed to change in brightness repeatedly and consistently. And he got very excited about this and famously wrote on this photographic plate that he took, var, for a variable star. The reason he was excited about it is because if you recall back to our previous lecture, Henrietta Swan Leavitt figured out that Cepheid variable stars can tell you the brightness of, you can use the period of these variable stars to figure out the brightness of the star overall, and therefore use that to figure out how far away this object is. So when Hubble measured this star's period with the telescope in California, he found that it was bright enough, and compared that to how much light he actually received, that this nebula had to be very, very far away, and therefore was as big as the Milky Way was expected to be. So Hubble was the one who eventually settled the debate in favor of Curtis, that these spiral nebula were in fact large enough to be galaxies, and indeed were made up of stars just like our own galaxy. So the Andromeda Nebula is actually the Andromeda Galaxy. So yeah, so using the Leavitt law, Hubble showed that Andromeda is far away and must be its own galaxy made up of stars. So here's a nice couple of images to compile it to show this object. So on the left here is a modern image of the Andromeda Galaxy. You can see that there are these kind of beautiful bands of gas and dust, which are similar to the bands that we see in our own Milky Way, except instead of looking at them from afar, we're looking at them from inside. So we see them as this band of gas and dust going all across the sky. On the bottom right is that image I just showed you of Edwin Hubble's photographic plate, where he noted that this star was a var, a variable. And in the top right is an image from the Hubble Space Telescope, which was named after Edwin Hubble. And the Hubble Space Telescope took this image of this particular variable star, which Hubble, the person, named V1. And you can see it here. It's this slightly brighter star in the circle. What you can see in the new modern space telescope image that you couldn't see in any of these others is that there are just tons and tons and tons of other stars visible. The only reason why this one stood out was because it was a little bit brighter. But look at all of those red and blue specks in that Hubble Space Telescope image. Andromeda is just like our own galaxy. It has billions of stars of its own. It's its own island universe.